Okay, let's go ahead and review this homework. So when you get right down to it, when you're measuring the temperature of a substance, you're measuring the blank of the substance molecules. Speed. So temperature is really a measurement of the speed at which those molecules are vibrating or moving around. Speed. Anybody else have anything else they wanted to throw in there? Besides speed or movement? Yeah. Velocity? Sure. Okay. What do we got here? You had 475 and 675, and it's aluminum, and starting temperature of, what's the final temperature? Why is this one kind of a pain in the butt?
Because you have to convert the Fahrenheit to Celsius.
We can't do the problem with Fahrenheit because the specific heat value is in degrees Celsius, right? So it's 71 degrees Fahrenheit. About what Celsius-ishness should we get? 22? 20 is real close to 20, right? Okay, so if I go 71, and then I have to multiply by 5/9, and then subtract off 32, what do we get there?
22.
Is it 22?
Yeah.
Okay. All right, so I got 22 degrees Celsius, and that's my final temp. So what I'm looking for, or no, that's my initial temp. I'm looking for my final temperature. All right, well, let's figure out how much the temperature changed. The is aluminum 0.22?
Yeah.
All right, so the specific heat for aluminum is 0.22 calories per gram degrees C. So I need a temperature here. So I'm going to take grams times degrees C divided by 0.22 calories. And then I'm going to get rid of the grams by putting 675 in the denominator, so the grams cancel. And I'm going to put 475 calories in the numerator, so those cancel out. And that's kind of funny. And so I'm left with degrees C. And somebody have a number?
3.2 degrees Celsius.
That's it? 3.2 degrees Celsius? Okay.
70, 23, 70.
I'll just knock it out here. 475 divided by 0.22 divided by 675, 3.2. So what did we just calculate? What's the 3.2? The change in temp. So I added this 475 calories to the 675 grams of aluminum, and its temperature went up 3.2 degrees. Okay. If my starting temp is 71 degrees, then my final temp is going to be what?
77.
Oops. Oh, that's wrong. Let's go with 22 degrees Celsius plus 3.2 degrees Celsius, and we end up with 25 degrees Celsius. What happened to the 0.2? The sig figs goes away. Okay, so 25 is our answer. Do we have a definition for an isotope?
All atoms and neutrons are charged. Equal numbers of protons and
It's okay. That's not enough info. Say again? Okay. How about same number of what? Protons. And not same number of what? Neutrons. So it's the exact same element, it just has a different mass because the number of neutrons is different. Allotropes?
Same molecule, different number of atoms.
Don't say molecule though. Same atom.
different combinations.
I like that. Big part right here with itself. Good job.
An example is O2 and O3.
Yep. So I've got O2 and O3. So they're just oxygen, but they're different combinations. One's a pair and one's a triad. Diatomics?
An
Oh.
element that's pure for itself.
Okay.
Example is H2O and O2 and
That's all of them. There are only 7. Explain what these people did to describe the atom. So what was it that Thompson did? This is a rehashing from last homework. Okay, so finds the electron. Anything else?
find out the ground.
No.
Have the phone for
No. The Pomponi model isn't correct. Of what he discovered that is correct is he found the electron and he realized that the electron can come off. The other stuff that he thought about wasn't quite true. How about Rutherford?
He said that the atoms are very small, densely
Missed some of that. You missed a piece.
They're very small, densely.
No, the beginning. No. The atoms have a nucleus that is small, dense, and positive. Sadi? Yeah, he figured out that the nucleus when Thomson and Rutherford realized that there was a nucleus, they only knew that it was positive. They didn't realize that that nucleus consisted of individual little pieces that are all grouped together. If they would have known that, they might have done some other work. But so that nucleus isn't just a chunk of positive; it's tiny chunks of positive protons all next to each other. How about
What's the word after matter?
naming them protons? You have a problem with my penmanship? So did every grade school teacher I ever had. Chadwick? Neutron. So he comes up with the discovery of the neutron. Bohr?
Planetary model.
I like that word, planetary or solar system. He describes that the electrons are located in some sort of planetary model which orbit around the nucleus. Turns out that to be correct. Still a convenient way to think about it sometimes, though. And then Heisenberg?
He proved Bohr wrong by half.
I like that. So we proved them wrong by using calculus and statistics,
Which is more or less quantum mechanics.
which turns out to be quantum mechanics. $33 years for the neutron. Why? No, we had the technology. One, most important, no one is looking. And the second reason? Lack of charge. Because there was no charge, there was a lack of charge on the neutron, no one noticed that it was there. Anytime that they did any interactions with electric fields or magnetic field, the neutron had no, there was no action by the neutron, so it was no, there wasn't anything to see. How about this table? What are we going to throw in here? 4 for the beryllium. So the beryllium has 4 for its atomic number. So what's that telling you about it? It's telling you it has 4 protons, and since you know it has 4 protons, then you know, now you know that it has 4 electrons. And since this one has 4 protons and 6 neutrons, then its mass is 10. So that number checks out for us. And then it's beryllium. Okay, so what element has 82 protons? No, lead. Pb, and then lead. And so if it's got 82 protons, what else does it also have? It's got 82 electrons. And this isotope of lead has a mass of 207. And since we know 82 of them have to be protons, then how many neutrons do we have? 125. So do all elements of lead have 125 neutrons? Nope, just this one and some other ones, but that doesn't mean they have to have 125. So what's OS? Osmium. What'd you say?
I said it wrong.
No, say it.
I said osmium. But I put
Osmium.
an N instead of an M.
Yeah, there's the I is after osmium. Very uncommon metal. When alloyed with iron, it makes the iron very, it makes it more structurally sound, but it also makes it more brittle. So it would be a more rigid structure, but the structure wouldn't be able to handle any sort of flexing. And osmium's atomic number is what? So 76 protons gives it 76 electrons. And since this one we're saying has a mass of 180 or 190, then what's left over is my neutron number, so that is 114 neutrons in this osmium. All right, so I've got this element radium, and the symbol for radium is Ra. And radium has how many protons? And so that means it's got 88 electrons. And so if I add the 88 and the 138, we get 226 for this particular isotope's radium's mass. Okay. We good with that? Alright, so you're driving your fast Mustang and you hit Canada and the speed limit says 125. Why should you not be so excited?
Miles to kilometers.
Yeah, they're talking about kilometers up there. So this is 125 kilometers per hour, not 125 miles per hour. So if I go one kilometer is 1,000 meters, and 1 meter is 100 centimeters, and 2.54 centimeters is 1 inch, and 12 inches is 1 foot, and 5,280 feet is 1 mile. Now I've got a speedometer number I can work with, and it's miles per hour. Somebody have a number for that? Should be like 60. 77.7?
It's 77 point some, it's a long number, but
Yeah.
it just goes 77 miles an hour.
No, you can't have 77. We got 125 up here. We got three sig figs.
77.7.
Is it continuing sevens, or what's after that 7? 77.7 what?
It was 77.67.
It was 77.67? Okay, that's good then. So then our answer would be 77.7 miles per hour, which is still pretty fast, but it's certainly not 125. If you didn't do it like this, you're not going to get full credit for it on an exam.
We can't, we have to do.
You have to do that. Why? Somebody tell me why. We were just discussing how many sig figs we had, and this is 3 sig figs here, right? How come we didn't talk about this 1? Why wasn't that part of the discussion? So? This thing right here is equal to what? No? 1. Is there any ambiguity in the fact that it's equal to 1? Why not?
Because any number times one is that.
No, no. How do you know that that number is equal to 1?
Because of the same thing.
They're equal to each other, right? So by definition, they're exact. So I don't need to worry about this because there are no significant figure issues here, because significant figures are an inaccuracy in measurement. This isn't a measured value. This is an exact value. How about this one here? Exact, exact, exact. What do you know about this one right here? It's exact. It says it in the book. They measured it to be exact. So do I need to worry about sig figs with that? Nope. What if you use the 1.609 kilometers per mile?
That's what I use versus about 77.7.
All right, well, I didn't actually do the math with this, but
But that's what
just because you use that and got the same answer doesn't mean that that's going to work every time. Is that particular unit conversion exact? That's my question. Have we talked about that being exact before? I've actually pointed out that this is the only unit conversion that is exact. So that means all the rest of them are not exact. So you can't use any of them except for this one when I'm converting from the English system to the metric system. Because in yours, you have to consider the significant figures associated with that conversion factor. Do you know what the significant figures are with that? You don't. So you wouldn't actually be able to answer the question with correct sig figs because you don't actually know what you're supposed to be writing down for sig figs. So let me just see if this works out. I'm sure it will, but 12 divided by 5,280. 776714. Okay. Well, someplace in a later decimal back here, that version that you use will be incorrect, where this one won't. Plus, I'm not going to give that one to you on the test. I'm only going to give you this one. All right, so you just dropped your new iPhone into the river, but it's wrapped in a waterproof case that's supposed to float. And the iPhone's mass is 135 grams, and the case's mass is 45 grams. What's the minimum volume for the case that would allow the thing to float? So I've got 135 and I've got 45, so that gives me a total mass of 180 grams. So this is my mass number, and since density is equal to mass divided by volume, and the density of water is 1 gram per centimeter cubed, if I put 180 in the numerator, and I need a number that is smaller than 1 over here, this answer has to be less than 1. What goes down here?
At least one.
Anything that's bigger than that, right? So 181 centimeters cubed would work. Anything larger than 180 is going to work for you. So if the case's volume is 181, then that makes the density less than 1, so then the case will float. So what if the case's volume is 150? It's gonna sink. So somewhere in that Columbia River, there's an iPhone 4S in a perfectly good waterproof case. I'm saying that because it's mine, and it's somewhere. It came disconnected from the carabiner that I had attached to my board shorts, and it's, if somebody found it, I'm sure it would work just fine. It's been there for like 2 years, but the case has got a 10-year lifespan, and yeah, whatever. I'm sure there's other good stuff in that river too. All right.